The periodic table can be considered your cheat sheet for a lot of the general chemistry questions that you could come across on test day. That's because the periodic table is arranged so that we can easily pick up on the trends of the elements. My name is Alyssa, and this video is designed to help you become familiar with these trends and learn how to identify them on the periodic table. In this video, we'll look at a number of different trends, but we'll start off by looking at what the effective nuclear charge is. Then we'll see how it affects such things as the atomic and ionic radii, the ionization energy and electron affinity, and finally, electronegativity. After watching this video, you will be familiar with the properties of elements and how they are arranged on the periodic table. You will be able to answer questions relating specifically to the trends of different atoms or ions. The effective nuclear charge is the attraction of the nucleus felt by the electrons, and dictates many of the periodic trends tested on the MCAT. Since the nucleus is positively charged and the electrons are negatively charged, there is an electrostatic attraction between them, which forms the basis for the effective nuclear charge. An atom is composed of a positively charged nucleus and negatively charged electrons arranged into shells. The innermost shells are the non-valence shells, and the outermost shell is the valence shell that contains the valence electrons. These electrons are not static and are constantly in motion around the nucleus. Valence electrons are attracted to the nucleus, but are repelled by the electrons in the non-valence shells. Electrons in the non-valence shells shield the valence electrons from the positive nucleus, but overall, the valence electrons will experience an attraction towards the nucleus. This is the effective nuclear charge, denoted Z subscript EFF. We can estimate this value for an element by taking the number of protons and subtracting the number of non-valence electrons. This will give us a rough estimate of the effective nuclear charge of the neutral atom. Let's apply the effective nuclear charge calculation to elements in the same period of the periodic table: sodium, magnesium, and chlorine. We will use the atomic number of each to find the number of protons in the nucleus: 11 for sodium, 12 for magnesium, and 17 for chlorine. We then use the electron configuration of each element to identify the non-valence electrons. The valence shells of sodium, magnesium, and chlorine are all found in the third shell. That means that all the other electrons are non-valence. These are found in shells 1 and 2, highlighted in pink and purple here. Sodium, magnesium, and chlorine have the same number of non-valence electrons, 10, which we can substitute into the equation for the effective nuclear charge. For sodium, the effective nuclear charge is 1. For magnesium, it is 2, and for chlorine, it's 7. You can find this value easily by looking at the electron configuration and counting up how many electrons are in the valence shell. These values indicate that as we move across a period from left to right, the effective nuclear charge increases. This is because there are more protons in the nucleus as we move from left to right, but the non-valence electrons remain the same. So as we add more electrons into the valence shell, they feel a stronger force from the nucleus due to the increased positivity. Now let's examine what happens to the effective nuclear charge as we go down a group. For example, lithium, sodium, and potassium. We again use the atomic number to find the protons for each element. Take a look at the electron configuration for these elements. Lithium, sodium, and potassium are group 1A elements, so each has just one valence electron. This means that all the other electrons are non-valence. Since they are all neutral elements, the number of protons and electrons are the same. So if lithium has 3 protons and 3 electrons, and one of those electrons is a valence electron, then 2 electrons must be non-valence. Do the same steps for sodium and potassium to find the non-valence electrons. Solving the equation, it would appear that sodium, lithium, and potassium have the same effective nuclear charge. Just like last time, we can easily calculate this by looking at the fact that for any neutral atom, the effective nuclear charge will be equal to the number of valence electrons. However, this is not entirely true. Recall that as we move down a group, the number of energy shells increases, and that higher energy shells are farther away from the nucleus. With less energy shells, valence electrons are closer to the nucleus and feel a stronger attractive force than when there are more energy shells with valence electrons farther away from the nucleus. Even though the effective nuclear charge calculation is the same down a group, The real electrostatic force decreases down a group due to increasing distance from the nucleus.
Make sure that you're familiar with this trend, that the effective nuclear charge increases across a group and decreases down a group, because the effective nuclear charge is important to all of the other periodic trends that we will investigate in this video.
The atomic radius is the distance from the center of the nucleus to the outer boundary of the valence electron cloud. Note in this diagram where the nucleus, valence shell, and valence electrons are. The atomic radius is measured by examining the distance between the centers of two atoms, since it is impossible to know where exactly the outer electrons lie on an atom because they are constantly in motion. There are ways in which we can alter the atomic radius. Since there is attraction between the electron cloud and the nucleus due to the effective nuclear charge, we can increase the effective nuclear charge by adding protons while keeping the non-valence electrons constant. Adding more protons to the nucleus increases the attraction to the valence electrons and brings the electron cloud boundary closer to the nucleus, thereby decreasing the atomic radius. We already determined that the effective nuclear charge increases from left to right across a period. That means that elements on the right side of the periodic table have stronger poles on their electron clouds, and therefore the radius of these elements decreases from left to right, and the elements with the largest radii are found on the left side of the periodic table. Going down a group, the effective nuclear charge decreases and holds valence electrons less tightly. Because there are more and more energy levels and the effective nuclear charge is decreased going down the group, the largest elements are found at the bottom of a group as the atomic radius increases. The largest element that is commonly found in nature is cesium, the last element in group 1A, ignoring the extremely rare element francium. The smallest element is of course helium, because it is found at the end of a period and at the top of the group, where atomic radius is smallest.
We just explored the atomic radius of neutral elements, so now let's investigate the ionic radius that results when these neutral atoms lose or gain an electron to form an ion.
Ionic radii do not follow typical periodic trends. Let's use the effective nuclear charge to predict the trend in ionic radii. Consider fluorine, neon, and sodium. As neutral atoms, according to the periodic trends, of the three, neon would have the smallest radius and sodium would have the largest radius. The ions will not follow these trends, but we can use the effective nuclear charge to visualize this. Fluorine will gain an electron to reach the stable electron configuration of neon, and sodium will lose an electron to reach the neon configuration. At this point, they will all have the electron configuration of neon. We can still use the atomic number to find the protons, and since all three elements have the same electron configuration, they will have the same number of non-valence electrons. The second energy shell is the valence shell, so the two electrons in the first shell are non-valence, and this is inserted into the equation. Solving, the fluorine anion has the lowest effective nuclear charge, while the sodium cation has the highest. The effective nuclear charge is inversely related to atomic radius, so the fluorine anion would have the largest atomic radius, neon the second largest, and the sodium cation would have the smallest radius. Keep in mind this important takeaway. Anions will generally have larger radii than their neutral atoms, and cations will generally have smaller radii.
Now we will examine the trend in the ionization energy of elements.
Ionization energy is the energy required to remove a valence electron from an atom. This process requires energy in order to counteract the attraction the electron feels to the nucleus. Therefore, it is an endothermic process. Consider calcium. Neutral calcium has 20 protons in the nucleus and 20 orbiting electrons. The electron configuration of calcium, as well as the diagram above, indicate that 2 of these electrons are found in the first shell, 8 are in the second shell, 8 in the third shell, and 2 are in the fourth shell. Since calcium has the same number of protons and electrons, the charge is neutral, or 0. Take a close look at what happens to this valence electron. The first ionization energy is the energy required to remove an electron from a neutral atom. When we remove the electron, 2 important things happen. First, we lost an electron from a neutral state, So we now have one more proton than we do electrons, and the atom has become a cation with a +1 charge. Second, the electron configuration also changed. Our calcium atom now only has one electron in the 4s subshell. Now have a look at this last remaining valence electron. The second ionization energy is the energy required to remove an electron from a +1 cation. If we were to remove a second electron, we have to contend with additional electrostatic attraction between the +1 atom and the negative electron. This means that the second ionization energy will always be greater than the first. When we remove a second electron, the atom is now +2. For group 2a elements like calcium, removing a second electron gives a noble gas configuration state. This is a stable state that atoms like to be in, so the third ionization energy for calcium and other group 2a elements will be exceptionally high because more energy will be required to remove an electron from this stable state. Since ionization energy is determined by the electrostatic attraction between the nucleus and valence electrons, the trend of ionization energy follows that of the effective nuclear charge. Helium has the highest first ionization energy, while cesium has the lowest first ionization energy. Group 1a elements like sodium have exceptionally high second ionization energies because group 1a cations are in a noble gas electron configuration. Group 2a elements have exceptionally high third ionization energies because group 2a 2+ cations are in a noble state configuration.
Now that we are familiar with ionization energy, we can easily introduce the trend of electron affinity, which is in fact the opposite of the ionization energy.
Electron affinity is the energy released when an electron is gained by an atom in the gaseous state. Just like in the formation of a chemical bond, when two attracted species come together, when a newly added electron is drawn towards a nucleus, it releases energy. Even though an exothermic process has a negative enthalpy, electron affinity is reported as positive because it represents how much energy was released. Halogens in group 7a have the highest electron affinity. Let's look closely at what happens when fluorine gains an electron. Looking at the electron configuration, we can see that the addition of an electron gave fluorine a stable noble gas configuration. This is a very favorable outcome. Halogens only need one electron to reach the noble gas configuration, and since this is so favorable, it makes the electron affinities high. Since the atom is gaining an electron, the effective nuclear charge must be strong in order for the gaining of an electron to be favorable. This means that the effective nuclear charge and the electron affinity have the same trend. As effective nuclear charge increases, the electron affinity increases as well.
The last trend that we will cover in this video is electronegativity.
Electronegativity is a measure of the attractive force that an atom will exert on an electron in a chemical bond. Electronegativity is the basis for bond dipoles because if an atom with a lower electronegativity is bonded with an atom of high electronegativity, the electrons in the bond will spend more time orbiting the atom with the high electronegativity. Let's look at the bond dipole in a molecule of hydrogen fluoride, a covalent compound. From the periodic table, we know that hydrogen and fluorine have very different effective nuclear charges, low for hydrogen and high for fluorine. Because the bonding electrons spend more time orbiting the atom with a higher effective nuclear charge, the electron density in this atom is greater. The greater electron density induces a partial negative charge on the atom, while the atom with the lower electron density obtains a partial positive charge. Since the ability to pull an electron towards the atom depends on the attractive force from the nucleus, electronegativity follows the same trend as the effective nuclear charge, and the most electronegative atoms are found in the upper right of the periodic table. Nitrogen, oxygen, and fluorine in particular are the most electronegative elements. To remember this, think of hold the phon, F-O-N. Sounds a little like hold the phone, doesn't it? The most electronegative atoms hold electrons closer to them in a chemical bond, and these atoms are fluorine, oxygen, and nitrogen, F-O-N.
Since these elements are so electronegative, when they form bonds with a hydrogen atom, these molecules can undergo hydrogen bonding due to the large dipole that results from the difference in electronegativity between either of these elements and the hydrogen atom.
Noble gases, on the other hand, do not typically have associated electronegativity values because noble gases typically don't form bonds. Now that we are familiar with the trends and how we can recognize them on the periodic table, let's do some practice questions. This question is testing your knowledge of atomic and ionic radii. Go ahead, use your periodic table cheat sheet to help you with this question. The answer is B. Our answer choices give us 2 cations and 2 neutral atoms. From periodic trends, we know that the neutral sodium atom will be smaller than the neutral potassium atom. We also know that the sodium cation will be smaller than the neutral sodium atom, and that the potassium cation will be smaller than the neutral potassium atom. From this, we can eliminate answer choices A and C. The solution ultimately comes down to whether the neutral sodium atom or the potassium cation is smaller. Think about this. The potassium cation has the same electron configuration as argon, which is in the same period as sodium. Sodium is larger than argon, and the potassium cation should be smaller than argon because it has the same number of electrons, but 1 more proton. Therefore, the potassium cation must be smaller than the neutral sodium, which leads us to answer choice B. This question is asking you to think about ionization energies and how this value changes through the first to third ionization. The answer is D, rubidium. Recall that ionization energy is the energy required to remove an electron. Exceptionally large changes in ionization energies occur when we take an electron from a stable electron configuration. The gap between the first and second ionization energy is over 2,000 kilojoules per mole. The gap between the second and third is just over 1,000 kilojoules per mole. The only reasonable explanation for this pattern is that the element must be stable after losing 1 electron, which causes the second ionization energy to be exceptionally high. Therefore, we need a group 1A element, and looking at your periodic table cheat sheet, you should be able to see that rubidium is in this group and is therefore the correct answer. This question is asking you not only to think about electron affinity, but also tests your skills in writing electron configurations as well. The answer is A. Recall that electron affinity is the energy released when an electron is gained by an atom. Therefore, elements that want to gain an electron to reach a stable electronic configuration will have high electron affinities. Group 7A elements have high electron affinities because they need just 1 electron to reach a noble gas configuration. We can eliminate B and C because these electron configurations are not of the halogens. Now recall the trend that electron affinity decreases as we move down a group. We can eliminate D because there are more energy levels in this atom, and therefore it is found further down the group than the atom represented by answer choice A. Excellent work if you got those questions correct. In this video, we looked at some very important periodic trends that you will need to be familiar with for test day. We defined the effective nuclear charge as the attraction between the nucleus and the valence electrons, and the atomic radius as the distance between the nucleus and the outermost electrons. The ionization energy is the energy required to remove an electron from the valence shell, and the electron affinity is the energy released when an electron is added to the valence shell. We finished off by defining electronegativity and how much an atom pulls electrons towards itself while in a chemical bond, and took note that fluorine, oxygen, and nitrogen are the most electronegative atoms. The periodic table can help us visualize these trends. The effective nuclear charge, ionization energy, electron affinity, and electronegativity all increase going up and towards the right diagonally across the periodic table, while increasing effective nuclear charge causes the atomic radii to increase in an opposite trend. From these trends, we also saw that elements on the right side of the periodic table tend to gain electrons in order to reach a stable noble gas configuration, and elements on the left lose electrons to reach stability. Thanks for watching this video, and good luck studying for your MCAT.